Scientists just made atoms exist in two places at once, on purpose, to hunt dark matter.
Okay, I'm sorry. Two places at once?
Two places at once. That's not a metaphor. That's the actual mechanism. And it just cleared a massive technical hurdle nobody had solved before.
Hold on. I need to... Okay, start from the beginning. What even happened?
So researchers at Imperial College London published a paper in Nature on June 17th. They've demonstrated a working prototype of something called a differential atom interferometer, and it's built around strontium-87 atoms.
Strontium. Like the element?
The element. Fermionic strontium-87, specifically. And here's the thing. This isn't just a cool physics demo. This is the first experimental proof that a key principle behind the next generation of dark matter detectors actually works.
The first proof. Like nobody had done this before.
Nobody. That's the headline. Imperial's own announcement calls it overcoming a major obstacle in the search for dark matter and gravitational waves. Those are their words.
Okay, so I'm gonna need you to explain, like, slowly, what an atom interferometer actually does, because that word is doing a lot of work right now.
Right. So the basic idea, you use lasers to put atoms into a quantum superposition. You're forcing a single atom to effectively travel two separate paths at the same time.
No.
Yes. And then you bring those two paths back together. And when they recombine, you can measure incredibly tiny changes in the atom's motion. We're talking sensitivity that makes existing instruments look like a ruler from a dollar store.
That's insane. And the dark matter connection is what exactly?
So there's a class of dark matter candidates called ultralight dark matter, really low mass, interacts super weakly, conventional detectors, even LIGO-style laser interferometers, they just can't see it. They lose sensitivity in the frequency range where this stuff would show up.
So there's this whole blind spot.
A huge blind spot, and very long baseline atom interferometers are specifically designed to operate right in that gap. According to the Nature paper, they're targeting frequencies where ground-based and spaceborne laser interferometers both lose sensitivity.
So they're not replacing LIGO. They're filling in the parts LIGO can't see.
Exactly, and gravitational waves too, by the way. Same instrument, same frequency gap.
Okay, but here's my question, and maybe I'm being slow here. Why wasn't this already working? Like, what was the obstacle?
Okay, so this is the part that genuinely surprised me. The big problem with very long baseline setups is laser phase noise.
Meaning the lasers get messy?
Messy is a good word. Over long distances, the laser light picks up random phase fluctuations. And in a single interferometer, that noise completely drowns out the signal you're trying to detect.
So you build this incredible sensitive instrument, and then the lasers just ruin it.
Ruin it? That's been the fundamental problem. But the differential configuration, having two interferometers running simultaneously, in theory those noise fluctuations cancel out.
In theory?
In theory. And that's what's never been experimentally confirmed. Until now.
Stop. That's the thing. That's the thing they proved.
That's exactly the thing. The paper says this provides the first experimental validation of the noise-immune measurement principle. They actually injected several radians of artificial laser phase noise per shot, deliberately making it worse, and the system still performed at the standard quantum limit.
Wait. They made it noisier on purpose?
On purpose, to stress test it, and it held up. No excess noise beyond atom shot noise, which is basically the floor, the physical minimum. You can't do better than that.
That's... okay, yeah. That's actually kind of beautiful.
And they also demonstrated recovery of coherent signals across a broad frequency range, under fully phase-randomized conditions. Meaning even when the laser phase was completely scrambled, they could still pull out a real signal.
I genuinely didn't know that was even possible.
Hang on, though. I want to be fair here. This is a prototype, a tabletop demonstration. The jump from this to a full dark matter detector is not small.
Okay, but isn't that always how it goes? Like every massive technology starts as a thing in a lab that barely works.
I mean, yeah. Okay, yeah, I'll give you that.
Because here's what gets me. They're not just dreaming about a bigger version. There's an actual plan.
The project is called AON, the Atom Interferometer Observatory and Network, led by Imperial, but it's a collaboration across multiple UK institutions. And the next step is AON 10.
10 meters.
A 10-meter baseline detector planned for the Beecroft building at Oxford. And they're targeting data collection before 2030.
Before 2030. That's not a far-off dream. That's 4 years.
It's funded through UKRI's Quantum Technologies for Fundamental Physics scheme, managed by the Science and Technology Facilities Council. So there's real money, real infrastructure, real timeline.
And then, presumably, it keeps scaling? Like 10 meters is step 2?
That's the roadmap. You go from tabletop to 10 meters to potentially much longer baselines. The sensitivity scales with the baseline length.
So, the bigger you build it, the deeper into the universe you can see.
Essentially. And remember, we've never directly detected dark matter, ever. We know it's there because of gravitational effects. But actually catching it? That's still an open question.
One of the biggest open questions in all of science.
And this experiment just proved that the fundamental noise problem, the thing that was blocking this whole approach, is solvable.
That's the sentence. That's why this matters.
Dark matter's been hiding for decades. Might be running out of places to hide.
I love that. Okay, forward look. What are we watching?
AION 10 construction progress is the near-term thing. If they hit that pre-2030 timeline, that's when you'll see real sensitivity numbers, real constraints on dark matter models, and watch for whether other countries start building competing detectors.
Because the UK doesn't get to own dark matter detection forever.
Nobody owns dark matter. That's the problem.
Okay, bottom line, a prototype in London just proved that the noise problem blocking next-generation dark matter detectors is actually solvable. Published in Nature, first of its kind, and a 10-meter version is coming to Oxford before 2030.
Quantum sensors are quietly becoming one of the most consequential fields in physics. This story is why.
If this got your brain going, honestly, same. Hit subscribe so you don't miss what comes next. We're on every platform, and if you want to go deeper, all the sources are in the show notes, straight from the Nature paper and Imperial's own research pages.
We'll see you tomorrow.
Don't let the dark matter get you.